Okay, so welcome everyone to Comp 2804, Discrete Structures 2. If that's not the course that you're here for, then there's the door, but hopefully you're all in the right place. So today I want to do a introductory lecture where we'll see a few of the concepts that this course is about. Nothing too heavy, but maybe get you thinking about some of these things. But before I do that, there's a few administrative things to deal with. So first up is me. My name is Pat Morin. I'm the lecturer for this course. My office is in 5177 Hertzberg. And this is how I prefer to be addressed, by my first name. So if you need me, if you want to get my attention, just call me Pat, not doctor or sir or mister or professor. I don't really like any of those names. And if you're not comfortable doing that, calling me by my first name, then just figure out a way to get my attention without saying anything. Catch my eye or put up your hand. That works well. I know that for a fact because I'm very bad at remembering names, so I constantly have to talk to people and get their attention without calling them by name because I don't know it. And you'll see that when we interact in class, I'll do that to you because I don't know most of your names. Okay. Second, sort of administrative detail that I have to talk about always is the grading scheme for this course. There will be assignments, 4 of them I think, that are worth a total of 25%, a midterm exam worth 25%, and a final exam worth 50%. So the thing to look out for here is this weighting doesn't represent the amount of effort that you need to put into these things. So the best preparation for the midterm exam and the final exam is actually doing the assignments. So the more effort you put into the assignments, both before they're due, working out to solve the problems on the assignments yourself, and after they're due, reading about what you got wrong, what you got right, and looking at the sample solutions and studying and understanding those, the better you will do on the midterm and final exam, because that's really your preparation. So don't skimp the effort on the assignments because it's only worth 25%. It's very unlikely that you will put 0 effort into the assignments and then still get 75% in the course. Okay, and 2 other things. If you're all registered in this course, you all have access to the CU Learn page for this course. And if you go there, what you'll find is that there's almost nothing there. There's only two useful things there, or three of them. There's a forum that you guys can use to talk to each other and the TAs and me to ask questions about material in the course. So feel free to do that. It's a very helpful thing, and it's probably the fastest way to get answers about things, because if you're trying to get an answer from me, well, there's only one of me, and I'm teaching about 400 students this semester, and there's only a handful of TAs, but there's hundreds of you guys. So most likely, if you ask a question on the course forum, many people in the class will see it before any of the TAs do, and they can offer either their advice or their commiseration, depending on what they have to offer. So the forum is one of the things that CU Learn is useful for. The other one is you need it for submitting assignments. So this is a course about mathematics for computer science, but at its core, it's a math course. So your assignments are not programming assignments. They're basically solving problems on pen and paper, or writing them up with LaTeX. I'll talk about that in a minute. But ultimately, what you submit for an assignment is a PDF file with your answers. There's a few ways to get a PDF file. If you are working with pen and paper, then I recommend you do a quick search for scanner apps for your phone that create PDFs. There are several of them, including some free ones that work quite well. So you just basically point your phone at a sheet of paper, and it'll crop it down to a nice thing and store that as a PDF file. So you can submit them that way. The other thing you can do for assignments that may be worth your while is to learn the LaTeX typesetting system. So you can nicely typeset your assignments to get beautiful mathematical formulas and actually just beautiful typesetting in general. And that's sort of a useful exercise because you get an extra technical skill out of it. And it turns out that LaTeX now, at least the math language in LaTeX, is sort of becoming the de facto language for computers and mathematics. So nowadays, on the web, for example, people write math using LaTeX and MathJax. And even things like Microsoft Word now have equation editors that use LaTeX. I can give you an empty LaTeX file to start you off if that interests you. Send me an email after class, and I'll post that on the webpage. One that has, I mean, they're sort of trivial. One that sets the margins a reasonable way and adds a header, that kind of thing. But send me an email to remind me to do that. Okay. Forum, submitting assignments, and the third thing that it's useful for is it's the link to the real course webpage. And the real course webpage is sitting in a server in our lab. And the reason that I don't want to use CU Learn as the real course webpage is CU Learn and these other content management systems that universities use, it's basically a paywall. It's something that prevents anybody who's not registered in the course, meaning they haven't paid their fees to register in the course, from accessing this material. And I want the material that I prepare for this course to be used as much as possible by anybody anywhere in the world, independent of whether they're registered in this course. So And the bonus feature of that is, well, once you go to that web page once, you can, I guess nobody bookmarks anymore, but your browsing history will remember it, and it's trivial to get there without a login. Okay. And what you will find on this web page, starting hopefully in about 2 hours, are all the things that happen in class. So all of the list of topics broken down by the day that they were taught. You'll find a link to the textbook, which is a free textbook. You'll find a link to a Comp 1805 textbook, which has background material for those who need to review it. And you will also find videos of these lectures. So you'll see there's a cameraman in the back of the class recording me now. The idea is that I take that camera with me back to my office after class, and about 20 to 30 minutes later that there'll be a YouTube video with the lecture on it. Now, I don't claim that I'm not doing this because I'm a fantastic lecturer, and we're certainly not putting a lot of production value into these videos. They will just be the raw lecture. What they're useful for, though, and I've done this many times in the past, is as a reference for you guys. So when you're in class, I would like you to be paying attention and trying to follow what we're doing in class, stopping and pausing, asking me a question if you need clarification about something, and not just furiously is taught at 8:30 in the morning, and I suspect many of those people won't be making it to class. Instead, they'll be watching the video. Okay, so I think that's it for administrative details. Is there anything anyone would like to ask me? Yeah. So my office hours are posted on the web page, but they're Tuesdays from 9 to 11. The TAs also have office hours. Basically, there's someone available roughly 2 hours every morning and 2 hours every afternoon, Monday to Friday. The times vary a little bit, but the schedule for those is also on the course web page, starting next week. Any other questions? Comments? Okay. Good. So today, I want to sort of introduce some of the kinds of things that we'll be considering in this course, the kinds of problems. And we'll start with a really sort of cute problem, or acute theorem or result that you can state informally this way. I'll write down the informal statement. So let's call this a pseudo-theorem. In any group of 6 people, we can find 3 people who are all mutual acquaintances, or they're all mutual strangers. Okay, so this says that you give me 6 people, you take 6 people from this class, and among those 6, I can pick 3 of them so that at least one of these 2 conditions is, one of these conditions is satisfied. Either those 3 people have never been introduced to each other, so nobody in that group has been introduced to anybody else in that group, or everybody in that group has been introduced to everybody else in that group. So, so underlying this, there's this idea of strangers and acquaintances. So these are the people who have been introduced to each other at some point in the past. So 2 people are acquaintances if they have been introduced to each other at some point in the past. And they're strangers otherwise if they've never been introduced to each other. Okay. So just to make things maybe a little more precise there, there's this notion that for any 2 people, they are either acquaintances or strangers. Okay. So in this model, there's nothing in between. So, and we try to sort of use language that kind of denotes this. Acquaintance doesn't mean friend. It doesn't mean anything other than you 2 have been introduced in the past. And stranger just means you've never been introduced in the past. Even if you've seen each other 1,000 times every day for the last 1,000 days, you'd still be strangers if you were not introduced. Okay? So there's this binary classification. For every pair of people, you can say, they're either acquainted or they're strangers. Okay, so does everybody understand the statement of the theorem? All right. So let's try to maybe put it in a language closer to something we understand. So let's draw a picture of this. So it's a theorem about 6 people. So let's draw those 6 people as little discs or circles. And, well, for every pair of people, there's a classification. Either they're acquaintances or they're strangers. So let's say that if 2 people are acquainted, then I will join them with a red line segment. So for example, maybe this person knows that one, and that one, and that one. This person knows that one, so only knows 2. This person knows that one. This one maybe only knows 1 person in the group. And those 2 know each other, and let's say even those 2 know each other. So that shows me who the acquaintances are among these 6 people. Clear what this picture means? So this is just an example. The theorem itself is a statement about every group of 6 people. This is one particular group that has this particular structure of acquaintances. Well, and since we said that this classification is binary, acquaintances or strangers, let me also explicitly denote who the strangers are. So I'll use blue to indicate that a pair of people are strangers. Okay, so that just means that everywhere where there's not, for every pair that are not joined by a red edge, there's going to be a blue edge. So this one is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So I can hear music coming from the hallway. I'm just going to close this door. It's not that I hate music, but it's a bit distracting to me. Okay, so there's the picture for this example. And now the theorem says, well, among these 6 people, we should be able to find 3 of them that either they make a blue triangle or they make a red triangle. So among those 3, every edge between that group of 3 is blue, or every edge between that group of 3 is red. Do you see such a group in this picture? So I don't know, we can call these things A, B, C, X, Y, Z. So somebody describe a monochromatic triangle to me in this group. Yep. A, Z, B. That's a red triangle. So that, according to our legend, means that these 3 people are acquainted. Any others? Yeah. A, C, Y. Yep. There's 3 who are mutual strangers. Yep.
B, Z, Y.
B, Z, Y. Yep, that's a red triangle. So there's lots of them here. Any others? ACX. A, C, X. No, from A to C is blue, and C to X is red. So those guys don't satisfy. Okay. All right. So this picture here with these circles and lines, do we have a name for these kinds of things? It's a graph, right? A graph is really a thing that has a set of vertices that we've been calling people up until now, and a set of edges, which are actually pairs of vertices well, we've been calling those things just pairs of people. And what we've done with this, so what we have here is a graph. There's a red graph that we can call the acquaintance graph that tells us which pairs of people are acquainted. So there's an edge between them if they're acquainted. And there's a blue graph called the stranger graph, which tells us which pairs of people are strangers to each other. And if we take all the edges of both graphs, well, what we get is the complete graph. So every possible edge is in this graph. It's just now that we've colored them red and blue. All right. So let's just state the theorem another way. if we color the edges of the 6-vertex complete graph red, blue, then we can always find a monochromatic. So mono means one, chromatic means color. We'll either find a red triangle or a blue triangle. These are just other words for the things we've already been talking about. All right. So that's the theorem. And that's the one theorem that we're going to prove today. All right. So how are we going to prove this? Well, let's do something simple and say consider any vertex, and let's call that vertex A. So here's A. A is one of my 6 vertices. This is a complete graph, so there's 5 edges leading out of A, 1 to each of the other things. Okay? So, there are 5 edges incident to A. If I look at this particular example, I see 1, 2, 3 red edges and 2 blue edges. Okay? So, since I'm interested in finding a monochromatic triangle, meaning one where all of the edges or among the blue edges, what would you guess? Among the red, just because there's more of them. Okay? And in this case, there's 3 red edges. Can I always, is it always true that I will be able to find at least 3 red edges, or maybe at least 3 blue edges? For just one particular vertex. Fix a particular vertex. Yeah? Yeah. Yeah. So if I count up the number of red edges incident to A and the number of blue edges incident to A, that's 5, right? And, well, if there's not 3 or more red edges, then there's at most 2 red edges. And if there's not 3 or more blue edges, well, then there's at most 2 blue edges. But if there's only 2 red edges and 2 blue edges, that would only make 4 edges incident to this thing. So it must be the case that one of red or blue is at least 3. So, either, let's say, at least 3 edges incident to A are, or at least 3 edges incident to A are blue. Okay. we conclude that at least one of these two things has to be true. In fact, exactly one of those things is true, but we only need at least one. Okay. Now I'm going to make a claim that we'll come back to later. Assume at least 3 edges, and we'll call them AB, AZ, and AX. AB, AZ, and AX incident to AR red. Okay? So this phrase, without loss of generality, we'll see it kind of frequently in this course. It's something you have to really look out for, both when you use it and when you see it written somewhere. So what it means is there are times when we have more than one possibility. In this case, we have 2 cases, at least 3 red edges or at least 3 blue edges. And when you say without loss of generality, it means that the 2 cases are essentially the same. So here, we can almost immediately see it that there's a kind of symmetry between red and blue in this picture, right? Every statement that we've said is symmetric about red and blue. So if I assume those edges, the majority of them are red, and I make some argument and I'm able to prove the existence of some monochromatic triangle, then exactly the same argument, changing the roles of red and blue, should also work to in the case when they're blue. We'll come back to that. We'll revisit that assumption later, just to make sure. But for now, let's assume that they're red, and we'll call those edges AB, AZ, and AX. Yeah. Yep. No, there's no such thing. The graph could be all red. Could be a clique of acquaintances, a group of 6 friends. Or it could be 6 people from different parts of the planet. They're all strangers. That's possible too. Okay, so now let's consider the edges BZX. So BZ, ZX, and ZB. So what are we looking at? We've got the magic X, Z, and B. And now we're interested in actually the triangle that these guys form. Let me get another color of chalk. So that's this edge, and this edge. Okay. So when I look at those 3 edges, I see blue edge, a blue edge, and a red edge. Did we find a monochromatic triangle already? Yep. There's no, oh yes, XB, you're right. XB. So did we, in those vertices that we're considering so far, do we see a monochromatic triangle yet? Well, what about this red edge here? So what do we know so far? Well, here's a red edge. Every one of these guys is adjacent to A using only red edges. So this red edge plus the two edges to A, that's a red triangle. Right? Agreed? Okay, so let's write that down. If one of BZ ZX or XB is red, then, well, and let's be clear that we're distinguishing different things here. If one of those things is red, then we can say without loss of generality, we'll assume that the red one is BZ. Then ABZ is a red cycle of length 3. Right? So the generic picture is I have A over here, 3 red edges coming out of it, and if there's a red edge between any one of these 3, then I get a red triangle that involves A. Right? 2 of the edges, that's that edge plus 2 of the edges that involve A. All right, that's good. So, among these 3 guys here, who have these unfortunate names, X, Z, and B, if I happen to see a red edge among those 3, then I'm done. I have found the red triangle that I'm looking for. Okay, so that's one case. What's the other case? What if there's no red edge among these 3? Yeah. Yeah, if there's no red edge among them, well, I know that there are edges among them, so they must all be blue. So that means the edge BZ is blue. It means the edge XZ is blue. And it means the edge BX is blue. But there's a blue triangle. So case 2 is if none of BZ, ZX, or XB is red, then BZX is a blue 3 cycle. Okay. So, in either case, we find a monochromatic 3 cycle. In one case it's red, in the other case it's blue. So that's it. That's the end of the proof. which will usually finish with either these three letters or maybe a filled-in box like this to say, okay, the discussion of this theorem is over. It has been proven now. So, any questions? Yeah?
So, is, like, you're using this specific example here, like, you just put that graph.
Yeah.
It's the reason that we don't understand, like, you don't have to show the form of the graph because of, like, when you say the loss of generality, that's basically what it's.
So I'm using this example as a sort of picture so that things stay clear in everyone's. If I don't have some working example, some people will just find it too abstract. But if we look at every statement that I've made here, they're not just true for this example. We've justified each one of them, right? So first statement says take any vertex. Can we take a vertex? Yeah, we have 6 of them, so we can take one of them. There's 5 edges incident to that vertex. Yep, that's true because the whole theorem is about complete graphs. If I take one vertex, it has 5 neighbors. That's true. Well, now those 5 edges, they're colored red and blue, and the number of red plus the number of blue is 5, so at least one of red and blue is 3. That's what this says. It has nothing to do with the example. And here we say, and now it's time to come back to this. Without loss of generality, let's assume that it's actually 3 red edges that we're able to find. Then we just have names for those vertices on the other ends of those edges. Here there's ridiculous names, Z, X, and B. And then we just look at the different colors that Z, X, and B could be. So in this particular example, we fell into case 1 where we found the. Okay. So this is not a proof by example, but it's really a general proof. This is an illustration of it. And usually when you're trying to understand these things, you wouldn't necessarily start with an example like this. You would start with what's known and then build it from what you're reading in the proof. So I might start by drawing 6 points and then say, okay, I believe this part about at least 3 are blue. Let's take this one with 3 neighbors and then see, okay, that's all I know so far, and just check it carefully that way. And you'll see that there's nothing in there that's not true about every instance. Okay, now, if you don't trust this without loss of generality business, we used it twice. We used it once here to say, let's say the majority of edges around A are red. And we used it actually here again, where we said, in this case, suppose there is a red edge, and just let's give it a name. Let's call it BZ, which, there's 3 edges in question here, and let's just say one of them is the one that's red. We also said that was without loss of generality. So why did we do that? Could we avoid it? And the answer is, yes, we could avoid it, but if we did that, here's what you can always avoid this without loss of generality statement, but here's what the proof would look like in this case. So you would say consider some vertex A, and then you would have case, let's call it R, at least 3 edges incident to A are red, and we call those edges AX, AZ, AB. And now we have to explore this case fully and prove it under this assumption that at least 3 are red, because later there's going to be a case B, which is at least 3 edges incident to A are blue. So this half of the proof we've kind of done. Then we break into two cases. Case A, which is, or if you like, case 1. At least one of AX, AZ, AB is red. And then if we want to be really pedantic, we have to break that into three cases, which are maybe AZ is red, or AX is red, or AB is red. And you see when you get to this level, you start to realize this is really silly. I mean, I'm saying, okay, if AZ is red, then, no, not this. XZ, ZB, or BX, and then you have to XZ, ZB, BX. And you see, okay, this is getting silly at this point. We're doing three things that are exactly the same. This is clearly without loss of generality. Then you finish that part of it. Then you come down here and you say, okay, oh no, we're still not done that. We still have no case 2. All of XZ, ZB, BX are blue. And in that case, we're done because we immediately found our blue thing. And now finally, you come back out to the top part where you're considering this other case. And you start writing this down, and you realize, oh, okay, this is also a waste of time, because now all we're going to do is write all this again, except wherever it says red, we're going to write blue, and wherever it says blue, we're going to write red. But it does happen often when you're discovering these proofs that you don't realize that you make a case distinction, and actually there is no real distinction there. It happens often exactly like we're doing here. Oh, you make this distinction between these three cases, and you solve the first case, and then you realize, oh, the second case is exactly the same, and the third case is exactly the same. Or you make the big case distinction and realize, oh, the second one is the same. So it's the kind of thing you learn over time. And then sometimes you can write a little bit more carefully so that the distinction goes away. Because, and a sort of trick for doing that is to avoid naming things until absolutely necessary. And you'll see that we already did this once. Because I could have started this proof with consider a graph with the vertices A, B, C, X, Y, Z. Case 1, consider A. I mean, that's silly because you don't need to, but you see you can make this thing blow up. You can make this thing blow up a lot, and conversely, you can sort of make it lean and clean as well. Okay. Yep.
Hey, I just wanted to check my vocabulary.
Mm-hmm.
So incident just means
Incident means, yeah, so in graph theory, we're a little bit picky about the words we use. Adjacent is something you apply to two vertices, and that means there's an edge between them. So A is adjacent to B. And incident is something you apply to a vertex and an edge, meaning that that vertex is an endpoint of the edge. Yeah. One is a relationship between two vertices. So these two vertices, A and B, are adjacent because there's an edge between them. This edge A is incident to the edge AB because it's actually an endpoint of the edge AB. So these are I'm not super fussy about that. If you are writing somewhere and you say A is adjacent to the edge E, no one's going to complain too much, but it'll somehow show that you're not an expert in the area. That's all that indicates. Yep.
I'm sorry, loss of generality just means given you have a, yeah.
So without loss of generality is just what you are saying when there would otherwise be a case distinction, like case 1, there's 3 red edges, case 2, there's 3 blue edges, but those 2 cases are completely symmetric in some sense, meaning that whatever you do to handle case 1, exactly the same thing can be done for case 2. And if you're unsure about whether some assumption is without loss of generality, then just don't make it. Make the case distinction, do both arguments, maybe later realize, oh, those actually were exactly the same, but at least then you won't be incorrect. Yep.
Sorry, just have a question about the earlier that you did for the three monochromatic set.
Yep.
The red. Are you making the assumption that if one of these Z
of algorithms, you always want to specify the base cases, the cases that are easy, where you don't really have to do anything, or you can just do it directly. And the obvious base case is n is less than or equal to 1. If I have an array that only has one value in it, then it's already sorted, right? There's nothing to do to sort it. It's already sorted. And if I have an array that has no values in it, then sure, that's already sorted too. We can just define that. Okay? In that case, you just return A. Otherwise, pick a random element x from A. So take your random number generator, pick an index between 0 and n minus 1, and take the element A. Call that thing x. Okay. So x. Let's say minus smaller than x. Plus the value greater than x. And the equal value equal. And you'll notice I added this word distinct here. That means that every element in the array is different from every other element in the array. So in particular, this value x is different from every other element in the array. So this third set here and then the last thing you do is return minus all the values smaller than x plus append to that the array that contains only one value of x, and then append to that what you get, the array that you get when you sort all the values that are bigger than x. So the picture looks like this. The thing that you return x, and all the things smaller than x, and all the things bigger than x, and recursively you've sorted these things. So these are in sorted order, they're all smaller than x, then you see x, and then you see the sorted list of things bigger than x, so the whole thing is sorted. And if you like to program in Python, this is like 2 lines. Really, really quick. With list comprehensions, really this second part here is 1 line of code, and this part is 2 lines if you break them. Very simple to implement. Now, is it a particularly fast algorithm? Well, let's look at the steps. So the base case is kind of boring and easy. This picking a random element from an array, that's easy. I mean, you use a random number generator to pick the element. Those tend to be fast. Then comes the sort of hard part, is you partition this thing, this array, into 3 sets: the stuff smaller than x, stuff equal to x, and the stuff bigger than x. Okay? And the only way I know of to do that is to compare every element to x to see whether it's smaller, bigger than, or equal to. So this step here, this partitioning step, means we perform n comparisons. With this value x that we're using to do the partitioning. Because what we had was, before we did this partitioning, we just had some array of stuff. X was in there somewhere. I don't know anything about the relationship of those things to x. Afterwards, it looks like this. All right, so that performs n comparisons. And then we make two recursive calls. One that sorts this part, and another one that sorts this part. Okay, so that looks difficult. And how long that takes kind of depends on, well, what the value of x was. I mean, where x landed in this final array. So what looks like a bad choice for x? What's that? The first element, so the smallest element in the array would be a bad choice for x. Because if I make that choice, then this picture doesn't look like this. But if x is the smallest value in the array, then after partitioning, I'll have x, and I'll have an unsorted list of all of the things that are bigger than x. If we started with n of them, that means there's n minus 1 of them left to do. So that would mean that I did n, I should be careful. The number of comparisons with x is n minus 1, so I did n minus 1 comparisons. And then I still had to solve this big problem of size n minus 1 recursively. Okay. So, and now, what if at the next stage, when I'm solving this problem recursively, I pick the smallest element that remains? Then I'm really in trouble, because then I will have done n minus 2 comparisons, and I still have a problem of size n minus 2 to solve. And this could go on and on and on and on like this. And if that happens, then we can quickly add up the number of comparisons. One is 2. Rough approximation. That is this number. But you get to divide by 2, so that's something. But that's not good, right? So that's somewhere around 50. Right, here's a billion. That's the 9 zeros is the billion. Oh, no, not 50, 500 billion. And I like to count things in the billions like this because modern processors operate in speeds that are measured in gigahertz. So a gigahertz is about a billion cycles per second. So you can think of, this would say that sorting a million elements, you can estimate at taking about 500 seconds. That's a lot of time to wait for that array to sort. So that doesn't look good. On the other hand, quicksort is very often the sorting routine of choice. Anyone know why? Yep. You can pick more than one pivot, but you don't actually need to. Yeah? Yeah. So it's right here. We say that quicksort picks a random element x from A. And then when we analyzed this sort of worst case thing, we said, well, what if it picks the smallest element? And then it picks the smallest element again, and then it picks the smallest element again, and so on. That's very, very unlikely, right? I mean, already if we start with a million elements, then the probability of picking the smallest one to be x is 1 over 1 million. And then to do that again is 1 over 999,999. I mean, and then again is, so that's a very unlikely thing to happen. Yep. Well, because when the array is unsorted, whatever value we pick doesn't tell us where it will go in the sorted array, right? So we have no information at that point. So instead, quicksort just picks a random one and hopes for the best. And so what we'll show later in this course, so this says that the running time of quicksort in the worst case is quadratic, is about n squared. And what we'll learn later in this course, and we'll analyze it very carefully, that actually, on average, it takes about n log n time. So again, with the case where n is a million, instead of taking 500 billion, it takes about 20 million. And 20 million is nothing, right? Less than a second. Okay. And the main reason for that is, well, what I've drawn up here is more typical of what happens when you pick a random element. In fact, it's pretty clear, I think, that if you pick a random one, then after you do your partitioning, half the time you'll be in this kind of situation where the random thing you picked is in the middle half of the array. There's at least a quarter of the elements here and at least a quarter of the elements here. And that's a pretty good split. Now, both problems are significantly smaller. Maybe the first one has 750,000 elements. The other one has 250,000, but that's still a lot smaller than a million. That's big progress. And that works out to then only having to take n log n time. So when we get to the probability section of this course, that's what we'll end up showing. But for now, for something fun to do, go ahead and fire up your Python editor and implement quicksort in 3 lines of code. And see how fast it is. In Python, that's a really sort of trivial exercise, but you can quickly test it on things of size 1 million. All right. So that's it for today. See you on Tuesday.